Here's that chapter 12 example we tried to do in class where the computers didn't work correctly. So I'm going to work the whole thing from start to finish. And I've updated my computer to the newest version of R, so you'll see what it looks like. If you're on a Mac, at this moment, it's 3.2.4. If you're on Windows, it's 3.2.5. And if you haven't installed the EZ package before, you'll have to upgrade first. All right, so we're going to do an ANOVA on some data we collected in class. And just as a reminder, what that data is we took a name countries by outline survey on Sporkle, and then we entered the scores for each group. And we are going to have a special issue with the fact that these groups aren't equal. Now, it's not something that'll come up on the test, but I'll show you how to handle that today. So the first step in any type of ANOVA is to deal with assumptions. So you want to say, is the data scale? Oh, sorry. The DV is scale, rather. And yes, it's a ratio scale. We could have gotten 0 of those countries correct. One of the next things is random selection. Kind of depends on what we decided that our population is. If the population is just my class, then we selected everybody and this is not an issue. But if we think about people in general, then we didn't randomly select. So excuse me while I let the crazy dog in the house. Right. Randomly assign, well, we could have, but I definitely didn't. So just to make things easier, we just assigned by a row, which is not random at all. All right, what's the next one? Normal? Well, don't know. Most of the things on those surveys are normal. We could have looked. They give you the normal distribution after, or they give you the distribution after they're done. And N is less than 30, so we can't assume. Last one is homogeneity, and we'll come back to it. Okay, so does it have equal variances? Not sure yet. We'll find out. So in step 2, the thing to do is to write down each group. So we had just 3 different surveys. And we want to know if anything is different between the surveys. So what we're doing is really looking for any differences somewhere. And so because F is folded over, remember, it's T squared, we always do a two-tailed or not equal to test. That's also because it would be really difficult to do greater than or less than, really, because there's no negatives. Since everything is squared, we treat everything as positive, but that's the positive and the negative end since it's squared, so we're doing a two-tailed test. Step 3 here is where we got stuck. First thing we want to do is list the means. We're going to use those means for that post-hoc table. But then we also want to include the source table that I've stuck in here. The problem with that is that EZ blew up yesterday. So let's walk through how to do that without it blowing up this time. So first thing I want to do, I'm going to close this, is import the data set. So I'm going to click Import Dataset from text file. Find that file here. I'm going to be sure, see down here has these V's, to click yes, so that the group name is at the top for every single one. Hit import. Okay. So you'll notice we have an NA down here. It's not really a missing value. It's just the way that we've laid out the data set in sort of wide format. We don't have their unequals at sample sizes. So we're going to have to deal with that here in a minute. So first thing we can do to get the means is take a summary of the data set. Make this a little bigger. Okay. So we can see, if we look at our output here, that we have 1 in A, but here are the means. So I've got 9.2, 9.2, and 7.3. So it's really unlikely that group 1 and group 2 are different, but maybe group 3 is different. We also want to get the standard deviations, but that's just to answer the homogeneity question above. Now for standard deviation, I can't do all of it at once. Like this will run, but it'll give you an error. So what you want to do is do one group at a time. So use the $ operator to get one column. The problem is when I run that, it gives me an NA. So here's an example where I have to use the na.rm, so remove nas, true. So I got 2.86. Because I like to do things without typing a whole bunch, I'm going to copy that twice and just change the name of the columns. Group 2 and group 3. When you do that, make sure they match over here. So we have 2.86, 2.22, 1.03. And you don't really have to copy these, but it won't hurt you, just so I know what you saw when you came up with this answer. Okay. And I'd say it's iffy because one of them is 2 times the other and one of them is almost 3 times the other. So I'd say probably not, but give me a reason. One is 2 times another group. Okay. And that way, even if I disagreed with you and I said, it's all right, you've given me a reason that's valid for, it shows me that you understand what the question is. So if you just put, these first 3, you can put yes and no. I think we got those now. But for this one, since it's pretty new, I think give me a reason. Okay. All right, especially if you're going to get it wrong. And then at least I can give you half credit for having the right reasoning, but the wrong answer. Okay, so the next thing we have to do to run the ANOVA is reshape the data. So we have the data in this format, and we want to put it into long format. So I'm going to load the reshape library. Reshape 1, not 2. And then I'm going to restructure the data. So I'm going to make the data long. I'm using the melt function. You put in the dataset name here. Measured equals, and then the names of the columns. Okay, so it does have to match. That needs to be a comma. There we go. It does have to match what's over here. So boop boop. It will give you this using ID as variables because we didn't use that parameter, and it just is telling you that it's blank. And now I have over here my groups. I got a little NA out here because of that one missing value, so it just restacked them all together. For easy ANOVA to run, I need a participant number. So what I want to do is add a participant number. Oops, not comma, equals, and it's 1 to in row long data. Okay. So that counts up 1, 2, 3, 4, 5, 6 to the number of rows that there are. And you'll notice now we have a participant number. Now, particular to this problem, but it won't hurt you to run this, because if it doesn't have this issue, it won't do anything to the data set. And NA omit, what NA omit does is it looks at any rows that have an NA, like this one, and omits them. I thought Easy ANOVA had that function built in, but it does not. So we have to exclude them before we run the ANOVA. Okay. That is, excuse me, one more. Okay, I'm good now. That is an issue with this particular package because obviously NA omit or NA remove is in other packages, or functions rather. And so all that will do is just take out those NAs. So it deleted the number of people. So that's probably a more accurate picture because we didn't really have 18 people. We had 17 people in one NA. Okay. And I'll include that in the code that you get for the exam. But that's a quick and easy way to get rid of all of your NA values if you have them. Even if Excel imported weird and has extra NAs, sometimes it'll do that to you. Okay, so now the fun part that we didn't get to do in class. So we're going to load the easy library. No problems. Woohoo! So the code is easy ANOVA data equals long data. DV equals what? Well, like we talked about in class, this isn't going to change as long as you call your data long data. When you melt things, it changes the DV into what's called value, so the value of the DV. Between, because it's a between subjects ANOVA, is variable, so between just tells it what column the group labels are in. Within subject's ID is participant number, so part no. And then type equals 3, so you get the right math. The last one we did was return AOV equals true, so we get more data, more of the information you need to make sure you have everything correct. So the fun part is, as long as you can get this line of code correct, and really the thing you're changing is the dataset name here on the columns, the rest of this code you can just cut and paste, and it will run without changing, because we have, we've called the data the same thing. Okay. Change the name of the dataset, though, you got to change this. All right, it does start me with a warning saying that the design is unbalanced because we have 5 people in one or 6. Yes, 5 and 6 and 6. So it doesn't like that, but that's okay. What we're really interested in here is this ANOVA section. So I'm going to cut and paste the whole thing, but I'll try to highlight the pieces we're going to use here. I'm going to stick it here. Okay. So DFD and DFN here, I said that backwards, but DFN and DFD, it's also here. So that's the same code. Are your degrees of freedom for between groups, that's DFN, DF numerator, so 2. My degrees of freedom for within groups, error or denominator is 14. Okay. 2 because it's 3 minus 1, 14 because it's 5 minus 1 plus 6 minus 1 plus 6 minus 1. That clearly makes the total 16. Remember here, you're not going to have anything or here or here. This Levine's thing we don't want to use at all, so don't get confused. Although the DFs are the same, Levine's is a homogeneity test that we don't really talk about in this class. F here doesn't line up very well. It looks much nicer here. Okay, it's right aligned. So, but F here is 1.47 is F. Stick that there. I get my p-value and this GES thing. We're going to come back to that too. So let me highlight. Let me try to highlight here. So we're going to use F, GES. Now the rest of these numbers come from here. So here's my sum of squares variable and residuals. So this one's variable is the front one. So 13.267 if I round up. And then 62.97. So obviously the total is them added together. So I could just add them together. 13.27 plus 62.97 equals 76.24. Now, I don't get mean square anywhere, but I could do this by hand, so I'll just divide. Let me open the calculator. So I've got 13.27 divided by 2, although I really should have just gone back to R, right, because it is a calculator, but 6.63, 4. You could also just use a regular calculator. 62.97 divided by 14, 4.50. And then just to make sure I've done everything correctly, I've got 6.64 divided by 4.5 is 1.47, which is where this number came from. Okay. So now I've filled in my ANOVA table. So mean squared error is the only one you have to calculate yourself. Okay. Now for step 4, what we want to do is calculate the cutoff score. So it's QT. I'm sorry, this isn't a t-test. QF. P-value first, or alpha. So let's 0.05, which is what we use in class. Degrees of freedom between, so 3 minus 1. Degrees of freedom within, 14. And lower tail equals false. Always, always, always on this one. So let's cut and paste that. Come over here. So our critical score is 3.74. Okay, our F value from step 3 here is 1.48. And then I don't know why there isn't a step 6 in my table. Okay, so fail to reject the null. Okay, there's no accepting of the null, it's reject or don't reject. Okay. What does that mean? That means there's no group differences. And so, in theory, if this wasn't an example to teach you how to do this, I would stop. And I wouldn't do anything else because I didn't reject the null. There's no group differences anywhere. So I don't need to investigate and figure out which ones, where they are, because there aren't any. So this is an example. I'm going to keep going. First thing we can do is look for effect size. Now, effect size is actually this GES thing. This stands for generalized effect size. But in a one-way between subjects ANOVA, it is mathematically the same to eta squared. So it's 0.17. And if you look at the rules for r squared, or eta squared, in this thing, either one, they're the same thing. 0.14 is large. So this is actually a large effect. So what does that mean? It probably means we don't have enough people. You don't have to say this. I'm just kind of circling back on some ideas that we've talked about throughout the semester to find the effect. Computer is unhappy with me. So that means not enough power. Right? So if we have a large effect and we don't reject the null, that probably means we don't have enough people. The other way you can calculate it is by doing sum of squares between over sum of squares total. So that's why we had to fill in our table here, 76.24, and that's where the 0.17 is coming from. Okay, so sum of squares between over total, not over error. Because it's a ratio of how much variance is due to groups and not individual differences or error. All right, to show you how to do the post-hoc part, what I'm gonna do is write in my groups. And in this case, it's like country 1 versus country 2, so it's unintentional that these have the same labels. And we're gonna do everybody to everybody else. I do not know what the funny spacing is about. Group 2 to 3. And I'm gonna write in their means. So group 1's mean was 9.2. Coincidentally, group 2's mean, if I round up, is 9.2. So that makes this easy. Group 3's mean, though, is 7.33. There we go. Okay. So are there significant differences anywhere? Let's see. Our comparison p is our alpha value, so we set that at 0.05. And we're going to use Bonferroni in a t-test. So this t-test thing, oops, up here please, is pairwise t.test. And then we're going to enter all the things we would have done for a independent t-test. So we're going to do dv first, so long data value. Grouping variable, long data variable. Hey, make this go away. Go away. There it goes. Paired equals false. Var dot equals true. Okay. And honestly, because we said homogeneity, we weren't sure. We really should do false here. But to make sure you all get the same answer and the one from the book, stick with var dot equals true. And then our p dot adjust dot method equals Bonferroni, which you do have to spell correctly. Okay, 2 R's, 1 N. And so remember, this is a t-test here. So that is the t-test code. If you look at your independent t notes, that's independent t right there. What we've done to make this a corrected t-test is add this pairwise adjust method. And what this does, this word here, pairwise, is it does all of them at once. So it kind of runs it quickly for you. So you don't have to do 1 to 2, 1 to 3. You don't have to do it 3 times. It's one line of code that runs all 3 of them. So I can cut and paste this into here. Oh, that gave me everything. Whoa, don't do that. How about just this? There we go. Okay, so let's see our p-value here. 1 to 2 is 1.00. 1 to 3 is 0.50. And 2 to 3 is 0.47. So we would not reject the null in any of these cases because it's not significant. Now that's going to match because We didn't find any significant differences using the irregular ANOVA, right? So no group differences here. So there aren't any here, but usually if you reject the null, you'll find at least one here. And if one of them is significant, you would look at the means. So I think what we're probably missing, because we have a large effect, is the differences here. But we have a small group of people. If we ran more people, those means might change. And so that is the Chapter 12 example with Easy ANOVA actually working, and how to write this up for the test.